Good morning to all of you. Welcome to the second lecture on the network series. In this lecture, we are basically discussed about KCL, KVL, dependent and the independent sources of the network elements. Since we have already been discussed about some basic issues regarding the inductor and the capacitor and the resistance in the previous lecture, now we have to be using these elements in the network circuits by using some principles that we are calling as a KVL, KCL, some basic terms, node, junction, branch and the mesh with their equations, and dependent and the independent sources. So this lecture is basically focused on the KCL, KVL and the dependent sources because it is very important in the network analysis. So let us discuss one by one what is the basic significance and terminology that we are using in the KVL and the KCL. Let's first go to the historical background of the KCL and the KVL. Gustav Robert Kirchhoff, a German physicist, stated two basic laws in 1847 concerning the relation between the current and the voltage in electrical networks. Scientist, German physicist was discovered this thing, how to make the easier solution of the networks by using the Ohm's law, and by using the KCL and the KVL law we can easily solve our electrical circuits by using this thing. So since Ohm's law is not sufficient to analyze the circuit, and there are some cases we have to be discussed that we are not able to solve the network circuit just by using the Ohm's law. However, when it is coupled with the Kirchhoff's two laws, we have a sufficient powerful tool for analyzing a large variety of the electrical circuits. So if we are solving the if we are solving the circuits, so we have to use the two basic laws, that first is the KCL law, second is the KVL law, in addition with the help of the Ohm's law. So let us discuss one by one what the laws is basically about. First we have to discuss about the Kirchhoff's voltage law. The scientist Kirchhoff discovered this law in the 1847 concerning about the relationship between the current and the voltage in an electrical circuit. It states that the algebraic sum of all the voltage sources and the voltage drop. Look at these two terms, voltage source and the voltage drop, very important, because with the help of this we can easily calculate the KVL equations. It's the algebraic sum of all the voltage source and the voltage drop in any closed circuit or a loop is equals to 0. What it indicates? Let us suppose draw some circuits. With the help of it we can easily understand the basic definition of the KVL. Let us suppose this is a circuit where we have to apply the KVL equation. It states that, I am just repeating for the sake of explanation, algebraic sum of all the voltage source. In this circuit there are basically three voltage sources that we are shown, V1, V2 and V3, and the voltage drop, and the voltage drop means R4, R1, R2, R3 and R4. Let us suppose there is a current I. So I into R4 is there is a voltage drop, I into R1 is a voltage drop, I into R2 is a voltage drop, and I into R3 is also a voltage drop. The algebraic sum of all the voltage source and the voltage drop should be equals to 0. So we have to write equations with the help of this law. So before writing it we have to follow some sign convention. Sign convention means in order to write the equations we have to follow some basic signs. There are two types of sign we are using. Let us suppose this is the battery that we have to write. It's having a voltage V1. If the current is going from this direction, let us suppose this is the direction of the current. So the first thing that we are assuming is that जिस डायरेक्शन में करंट फ्लो हो रहा है उस डायरेक्शन में आप उसका वोल्टेज मैग्नीट्यूड ले लीजिए. लेट अस सपोज अगर मैं इसका करंट डायरेक्शन चेंज कर देता हूँ इस तरीके से, ये प्लस है ये माइनस है, करंट अगर यहाँ एंटर कर रहा है, देन वी कैन से जो करंट है इस सर्किट के अंदर इधर फ्लो हो रहा है और साइन पहले क्या आया है प्लस का, दैट वी आर राइटिंग प्लस V1. सो फर्स्ट वी हैव टू एज्यूम द डायरेक्शन ऑफ द करंट, then by following the direction of the current, the sign that we have been obtained during the path of the current that we have to put. इसके पाथ में माइनस साइन पहले आया तो मैंने माइनस V1 लिख दिया. इस करंट के अगर मैं पाथ को देखूं तो प्लस साइन पहले आया तो मैंने प्लस V1 लिख दिया. तो मेरा एक साइन कन्वेंशन है. कुछ बुक्स में देयर आर सम बुक्स वी हैव बीन ऑब्जर्व दैट if we are moving from minus to plus then they will show the plus V1. It is always right. It is also be right, but it's our sign convention whatever we are want to have. According to me, according to some books, I have just been noted here that if we are going in the direction of the current, the sign that we are getting first that we have to write. In this current, the minus here is the first, then we write minus V1. In this section, the current is going this direction and the sign we are getting is plus, so we have write the plus V1. Now we are talking about the resistance sign. Let us suppose this is the resistance. If the current is going in this direction, put it plus or minus. It's having a, let us suppose resistance R having a current I. So we can say that VR should be equals to plus I into R. The current के direction में जो भी resistance आएगा और उस पे आप प्लस माइनस लगा दीजिए. This is the basic convention that we are following. Let us suppose if the resistance is like this fashion, if the current is going like this fashion, so we have put a plus and the minus, so we can say that VR should be equals to I into R plus. This is the basic sign convention that we have to follow in order to write the KVL equations in any electrical circuit in a closed loop. So this is basically a loop we have to follow and we are just applying the sign convention using the KVL equation. Let's start to write the equation. मैं यहाँ से start करने की कोशिश कर रहा हूँ. Here we have seen that the current is going in the direction, so we have put a plus minus as per our sign convention. जो जहाँ current जाएगा वहाँ plus minus आ जाएगा. It's already having a sign with a polarity of minus plus. Now the current is moving like this, so it's having a plus and minus. Then it's having a minus plus, then the current is moving like this, it's having a plus minus, it's having a plus and minus. Just applying the KVL equation we can easily write the equations. So current की direction में पहले साइन क्या आ रहा है प्लस का, then we have to write KVL equation in loop. So we can write the equation plus I into R4 माइनस V1, बिकॉज जो साइन आपके पाथ में आ रहा है वो आप ले लीजिए. यहाँ देख रहे हैं पहले क्या आ रहा है प्लस, यहाँ क्या आ रहा है माइनस, देन वी आर राइटिंग प्लस I into R1, then we are writing minus V2, it is having a minus, then plus I into R2, then minus V3, then we are obtaining I into R3 should be equals to 0. So this is the fundamental principle of the KVL, where we observed that firstly we have to assume the direction of the current. This is the first principle. Then we have to put the polarity in the networks like the resistance, inductor and the capacitance. Here in the case of resistance, so put the plus minus where the current is entering, put the plus minus, plus minus, plus minus and the plus minus, and write the KVL equation assuming the sign which is coming first we have to write. So this is the basic general equation of the KVL. Now we have to move towards the second law, which states that like this question. this is basically the KCL, Kirchhoff's current law. This law states that the algebraic sum of all the currents entering and leaving at node is equals to 0. What is significance? Let us suppose a circuit has been a node at this point. Node means where the junction or node, we can say that where there are two or more elements are joined, that we are calling as a node, where the current division is possible, that we are calling a node. So it states that the algebraic sum of all the currents, let us suppose this is a node where the current 1 is entering, where the current I2 is leaving. Let us suppose it is entering, it is also entering the node, or it is leaving the node. We can say that it is entering the node, or we can say that it is entering the node. So in any node there are basically, let us suppose 7 currents, which is some are entering and some are leaving the node. So we have to write an equation which shows that the algebraic sum of all the currents entering and the leaving at the node is equals to 0. What it means? It means that we have to follow the sign convention. What is the sign convention for it? Sign convention. Sign convention. Here I am using the sign convention. Let us suppose this is the node and this is the branch. If the current is entering the node, then we are put as a minus I. If let us suppose this is the node, where this is the node and the current is leaving through the node, away from the node, then we are put as a positive sign. So this is the convention that we are following. You can choose the alternative as a opposite sign. Some of the books have shown that if the current is entering, then they show the positive sign, and the current is leaving, they show the negative sign. It depends upon you, but my convention is that if the current is entering, it should be negative. If the current is leaving, it should be a positive quantity. So we have to find out how many currents are there which are leaving or which are entering. I1 is entering. KCL, if you put the KCL at node, then we can say that I1 is entering, should be minus I1. I2 is leaving, it should be plus I2. I3 is entering, it should be minus I3. I4 is entering, it should be minus I4. Or we can say that I5 is leaving, I4 is leaving, it should be plus I5. I6 is entering, should be minus I6. I7 is entering, should be minus I7, should be equals to 0. The summation should be equals to 0. This is the basic convention of to write the equation for the KCL. Mathematically, we can represent sigma. Let us suppose this is I, which I being a j, I1, I2, I3, I4 up to n terms. So j should be 1 to n should be equals to 0. This is the mathematical representation for the KCL equations. This is basically like this. Similarly, in the KVL equation, we can write the mathematical form. It should be the voltage drop. We can say that the voltage, it should be J, sigma J should be 0 to n, or it should be equals to 0. This is the basic mathematical expression for the KCL and the KVL. So I think you will learn about the concept of how to write the KCL and the KVL equation by using the sign convention. Now let's move on to our next part, then we can solve some numericals in the coming lectures. Firstly, we have to cover the basic issues. That first is the node, junctions, and some basic points. Let us suppose node, the definition. Some definition we have to learn. Node, branch, junction, and some general equations we can learn it after some time. Node is a equipotential point at which two or more circuit elements are joined together. What it means? Let us suppose a circuit is like this fashion. Let us suppose this is a circuit and we have to find the node. It is the equipotential point at which the two or more circuit elements are joined. Here we have seen that a circuit is shown like this fashion, where there is a resistance R1, this is R2, this is R3, R4, R5, 6, 7, and it is going to be R8. Now plus minus voltage, let us suppose 10 volt, it is 50 volt. So we have to find the node. What are the nodes are there in these circuits? So two or more elements are joined. Here we have seen that this is one element and this is one element, so this should be a node. This should be a basically node. A is the node because there are two elements are joined, the resistance element and the battery elements are joined, we are calling as a node. Here three elements are joined, it is a node. This is not a node because here there is no element is joined by this resistance, so this is not a node. This is a node. C is a node. This is also a node. D, because here the R3, R4, I5 are joined. This point is also a node because at this point the battery and this terminals are joined, so it should be E. This is a node because two or more resistance and this battery are joined together, so it's also a node. F, E, F, G, this is a node, and at this point is also a node because here in this point the battery and the resistance are joined together. So node basically signifies that two or more elements are joined, that we are calling as a node. Okay. So we have learned that the node is a point where two or more elements are joined. So the significance that we have to learn, this is a node, which is very important part. This is a node, this is a node, and this part is also a node. Now come to the next point that we are calling as a branch. It is a dead point on the network where the three or more circuits elements are joined. Three or more, three, not two. It is तीन से ज़्यादा होना चाहिए, तभी आप कह पाएंगे branch है. Three or more elements are joined, that we are calling as a node. Okay. So here we have seen that the B having a three elements, so it is a branch. I think between 2 points, I think there should be some error. This is basically a junction. This is the junction and this is the branch. I'm so sorry for it. Junction basically it is a dead point on network where three or more circuit elements are joined. So B is a junction, D is a junction, C is a junction, and G is a junction. So we have understand that the junction is a point on a network where three or more elements are joined. These are having a three element R3, R2 and R1. This is a junction. This having a three element. This is a junction. This is a junction. This is not a junction because there are two elements, 1 and 2. Two branches are connected. So there are four junctions in this networks. Let's move on to the next part. Next part we are having a branch. It is a part of a network which lies between the two junction points. Branch is basically नेटवर्क का वो पार्ट है जहाँ जो दो जंक्शन पॉइंट्स के बीच में होता है. ये जंक्शन है, ये जंक्शन है. दिस इज ए ब्रांच. BAHD इज ए ब्रांच. BD इज ए ब्रांच बिकॉज दो जंक्शन के बीच का पार्ट है. BC ब्रांच है क्योंकि ये भी दो जंक्शन के बीच का पार्ट है. CD ब्रांच है. CG ब्रांच है एंड DG ब्रांच है. दिस इज नॉट अ जंक्शन. DG is having a branch of R5, 10 volt battery and R6. So this is the basic understanding of the node. Node is a point where two or more circuit elements are joined. This is a node because their resistance and the voltage battery are joined together. Junction is a point where three or more circuit elements are joined. This is a junction, this is a junction, this is also a junction, and this is also a junction. Branch is a point of a network. It is a part of a network which lies between the two junction points. इस दोनों जंक्शन के बीच का ये पार्ट है, इसके बीच का ये है, and we can easily calculate the branch and junctions. Now we can move towards the general equation. This chapter we will discuss about after some time by using the nodal analysis. When we are learning about the nodal analysis, then we can come to this part and we will discuss. So let's move on to the some basic numericals for the understanding of the branch and junctions. Let us suppose this is the circuit. In the circuit configuration of a figure obtained, the number of nodes, junction points, branches and the mesh analysis. So we have already discussed what is the node, what is the significance of junction and what is the significance of branch. So by using this concept that we have learned, we can easily apply in this numerical. So we have to calculate the node. First we are calculating the node. As I already told you that node is a point, is a equipotential point at which the two or more circuit elements are joined. So here we have seen that this is the node because there are two elements are joined. So A is the node first, B is the node because there are three elements are joined, two or more, three are joined. C is the node because R2, R5 are joined. D is the node. This is A, B, C, D, E. E is the node because there are R6 and R7 are joined. F is the node because there is a three elements are joined. H is the node. Okay. Now G is the node because V and R8 are joined with the help of this node. So G is the node. And last we can say that A, B, C, D, E, F, G, H. So this is the basic nodes that we are having. 1, 2, 3, 4, 5, 6, 7 or 8. 8 having the nodes. Okay. Now we have to calculate the junctions. Junction point. Junction we have already discussed. It is a that point on a network where three or more elements are joined. So we have to find the three elements. So this is the junction because so B is the junction. We can say that B is the junction. Here two elements, so this is not a junction. Here the three element, this is a junction. Here the H is the junction, and we can say that the F is the junction. So here we have seen that there are four junction points are there. See, we have to calculate the branches. Branch we have discussed. It is a part of a network which lies between two junction points. Junction points के बीच का जो part है वो branch कहलाता है. ये junction है, ये junction है, तो branches is B, C, D is a one branch. This is a junction, this is junction. B, H is also a one branch. H, F, this is junction, this junction branch. D is the junction, so we can say that S, D is also a branch. B, A, G, H between two junction points. So B, A, G, H is also a branch. B, C, D, B, H, S, D, D, E, F. D, E, F is also a basically branch. 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. This is the basically branches that we have discussed. Now we have moved toward the mesh. Mesh is the closed loop path. So we have seen that this is the closed mesh 1. This is the also mesh 2, and this is the closed mesh which is called 3. So we have called it 3. So this is the basic part of to analyze the junctions and some basic issues regarding the analysis of node, junction and branches. Let's move on to our next part that we are having dependent sources and we are having the independent sources. Dependent sources and we are having independent sources. We know that in electrical circuits there are some symbol representation. If this is the symbol, this is we are also having some symbol. this having some symbol. This is the symbol, another symbol. This we having also symbol like this fashion. Like this fashion. So what it indicates? What is the significance of these symbols? This is not a voltage source, it is a voltmeter. We indicate the voltmeter. This is a current source. Sorry, it is not a current source, it is a ammeter which measures the value of current. This is basically a current source. This is basically a voltage source. This is also basically a voltage source. How we can analysis by just by seeing that this is a current source or this is a voltage source. This polarity indicates that it is a voltage source. This direction indicates that it is a current source. In these two systems, in these two symbols, we have not any direction, not anything that we are shown. So we can say that it is a V having a voltage meter and it is having a current meter. Rather than this, there are some another symbol that like this fashion we have to discuss here. It is diamond like ring. Sometimes we have seen that like this fashion, sometimes like we have seen like this fashion, with some marking KI1, or we can say that KV1, we can say that KVX, we can say that KVY, we can say that I2. So many things that we are already we have seen. Similarly, in the voltage source we have discussed, we have seen somewhere else like in the books KVX, KVY, KVZ, KI1, KI2, KIZ. So many things that we have already seen, we have seen in some books. So what is the significance of it? What we are calling as a K or something like this. In the current source we are using the current I. In the current source we are using a voltage V. In the voltage source we are using the voltage Vx, Vy, Vz and whatever the thing that we have seen in the books. Similarly, in the voltage source we have seen the current. So the significance of it, what is the significance that we are going to discuss? So the first thing that we have been having like shown here, voltage dependent voltage source. Let us suppose it is a network. Let us suppose this network is having elements. These elements having the resistance, inductance or capacitance, whatever it is a network, just representing the network. And this is the having dependent source. Dependent source always been shown by some diamond ring. This is diamond like shape and it's having a voltage source, so it is a plus minus because it is a voltage source and it is voltage dependent, so K times of Vx. So what is Vx? What is the Vx of it? This is the resistance and this having a battery like this fashion, and this plus minus we are calling as a Vx. So what is the indication of this Vx? So this indicates that this voltage source, because plus minus is shown here, depends upon the voltage. This voltage is been anywhere in the circuit, but this voltage source, the magnitude of this voltage source is totally depend upon the magnitude of the voltage where it depends. It depends upon Vx, and the Vx is anywhere in the circuit. In this circuit, here is the Vx. So we can say that this is the voltage source, voltage dependent voltage source. Let's move on to the next part, current dependent current source. Similar concept. Let us suppose this is the network we have shown. Voltage source is there. Let us suppose this is the resistance. Any circuit, it is just any circuit. This is the resistance. It's having a K times of Vx. It is a voltage source. Sorry, not K times. It is K times of Ix. And in this circuit, we have seen. Let us suppose this is the current which is flowing in this fashion, Ix plus minus 10 volt. So it is a voltage source because the polarity indicates it is a voltage source, but its magnitude depends upon the value of the current. So it is current dependent voltage source, and this current is always been present in the circuits and anywhere. Here in this circuit, this is the current Ix which is responsible for this voltage source. So it is a current dependent voltage source. Next, we move towards the same principle but to some another concept. We have seen the current dependent current source. current source. It is the current source. So current source being indicated by the arrow, and it is current dependent. So let us suppose KIX. This is the current source, and in this anywhere on the circuit, let us suppose the current IX is flowing. So this current source, basically arrow indicate current source, and this current source it is depend upon this magnitude of the current which is flowing in the circuit in any direction. So in this circuit the IX is flowing in this part, so it depends upon this current source. It is being depend upon this value of IX. Similarly, we can learn about the voltage dependent current source. Let us suppose this is a network, and we are just having a diamond like shape that we are calling as a dependent source. It is a current source, so it's having arrow, and it is depends upon the voltage. That means let's suppose KVX, and Vx is the voltage which is anywhere in the circuit as shown below. So let us suppose this is the voltage Vx, and this is the voltage which being depend upon this current source. So it is a voltage dependent. This current source is being depend upon this voltage magnitude. So it is calling as a voltage dependent current source. So this is the basic idea about the dependent sources. So I think you will observe some glimpse about how we can analysis and what kind of the sources they have. Just observe the polarity sign. If plus minus, that means it is a voltage source. If there is arrow, then that means it is a current source. Okay. Now next move on to the some numericals based on these dependent sources. Then we can easily understand how we can operate and how we can do some basic use about it. Let us suppose there is a one numerical which is being shown here. From the figure shown below, calculate the value of Vy. Here is the Vy that we have to calculate, and the given value is Iz equals to minus 3 ampere. This value is given to be a minus 3 ampere. So we have to calculate the value of the Vz. So Vz basically it is a voltage drop across the resistance, and I think the resistance value is 1 ohm. Okay, so we have to calculate the value of the Vy, and it is basically a voltage drop across the 1 ohm. So let's solution. We know that Vy should be equals to current I multiplied by 1 ohm resistance. So let us suppose this is the current I which is being flowing here, and we have to calculate the value of I. If we are able to calculate the value of I, then we can easily calculate this voltage drop. So if we are applying the KCL, before applying, just we have observed that this is basically 3Vx. So 3Vx, this arrow indicates that it is a current source which is dependent upon the voltage. So it is a voltage dependent current source. It is a current source which depends upon the voltage of the value Vx. So it is a so it is a voltage dependent current source. This is a current which is going like this fashion up to this point A, and this is the current Iz which is going like this fashion going towards the point A. If you are applying the KCL at point A, applying KCL at point A, we have observed that this is the point A. Here the current is like 3Vx. Here the current is Iz, and we are assuming current I. So our convention is, if the current is entering the node, is called negative sign. If the current is leaving the node, that we are calling as a positive sign. Here the applying the KCL, then we can write the equation. It is this 3Vx basically entering the node, so it is minus Vx minus Iz, and it is I is leaving, that should be equals to 0. So I should be equals to Iz plus 3Vx. Iz value is going to be minus 3 ampere, so I should be equals to minus 3 plus 3 into Vx, equation 1. So in order to calculate the value of Vy, if we are able to calculate the value of I, then we can easily calculate. But here is a dependency Vx. How we can calculate it? It can be easily calculated that in this circuit this 5 volt is in parallel combination with this voltage Vx. So we can observe that Vx equals to 5 volt. Put this value in this equation, then we can calculate the value of I. E equals to minus 3 plus 5 into 3. So we can say that I equals to minus 3 plus 15, it should be 12 volt. Okay, it should be a 12 ampere. Now put this 12 ampere in this equation, then we can easily calculate the value of Vy. So Vy should be equals to 12 into 1, Vy equals to 12 volt. This is our desired answer. Let's move on to the next solution. Here is the question. Now we have to find the current I2, and the I2 is flowing in this circuit, and the voltage V, and the voltage V, basically this is voltage V. We have to calculate I2 and the voltage V for the circuit shown below. Okay, here the circuit is shown here. We have seen that there is a one dependent source and one independent source. This is the basically called a dependent source, which depends upon the value of the current I2, which is flowing in this resistance R, and R having a voltage, the magnitude it is not shown. Okay, and this is the independent, so 21 voltage source. This I is shown here, this I2 is shown here. So there are two loops, or we can say that two meshes. With the help of the mesh rule analysis, we can easily calculate the value of V and I2. Let's suppose solve this question. This current is entering towards C node, so we can say that it is entering I, and the leaving current is I2. So we can assume that this current is I. By applying KCL at node C, I is entering, so it is minus I. We are assuming current I, which is leaving the node C, and the another current we are calling as I2, which is also leaving, that we are calling I2 should be equals to 0. So I we can easily calculate, it should be I minus I2. This we have to use. So we are just calculate the value of the I. So it's a thumb rule that in order to solve the any KVL circuit by using the KVL analysis, we have to first calculate the current in all the branches. This is the basic first rule. In the circuit, this current is not been given here, but just we are using the KVCL equation, and we can assume that this current having I minus I2. So we can easily use a KVL in this circuit, or we can say that in this circuit. So applying KVL in loop 1, let us suppose this is loop 1, this is loop 2, and we are having a sign convention that we have already discussed, that if we are starting from this point, this current is entering, so it is plus minus, so it is plus 2 into I. This is voltage source minus 3 into I2. It's having a plus sign, which is calling plus 3 into, here the magnitude of the current is I minus I2, plus this is 4 into I should be equals to 0. So we can say that, and the minus 21 should be equals to 0. We can solving it out. Let us suppose this is the 2I like this, plus 3I minus 3I2 minus 3I2 plus 4I2 should be equals to 21. And we can solve it. 5I4, this is minus 2I2 should be equals to 21. it is 4i, it is 4i, so we can solve it. 9i minus 6i2 equals to 21. This is our equation number 1. Now apply KVL in loop 2. Here is the loop 2. We just redraw here. मैं इसको फिर से ड्रॉ करने की कोशिश कर रहा हूँ. This is we are obtaining like this fashion. This is loop 2. ये 2 ओम है, ये प्लस माइनस V है, यहाँ I2 जा रहा है, यहाँ भी I2 है और यहाँ I माइनस I2 है. यहाँ I2 दे रखा था, यहाँ I2 अपन ने एज्यूम कर लिया. इट शुड बी I माइनस I2. बाय यूजिंग KCL we can easily calculate it. So applying the KVL in the loop 2. The current is moving like this fashion, so it's having a voltage drop, like we can say that it is having a magnitude of 6. It's having a 6 ohm. It's having a 6 ohm. So it's a plus 6 into I2. We are moving in this direction, but the direction of the current that we have already assumed in this resistance is opposite to our rotation. We are moving in a clockwise rotation, but we have already assumed a direction, or we can already find the direction of this current in this resistance is against our rotation. So it is minus. It should be minus 3i minus I2 should be equals to 0. 6i2 it should be equals to 3i minus 3i2. 9i2 should be equals to 3i. 3i2 should be equals to I. This is equation number 2. Put 2 in equation 1. Here this is the equation 1. We have to put the value of I in the equation 1. So it is 9 into 3i2 minus 6i2 should be 21. On solving, 21i2 should be equals to 21. I2 equals to 1 ampere. We have to calculate the I2. It is calculated. Now we have to calculate the value of V, and V is basically the voltage drop across this 6 ohm resistance. I2 is 1 and resistance is 6, so we can say that V should be equals to I into R. Here V equals to I2 into R. V equals to I2 is basically we have calculated 1 ohm into 6 ohm ampere should be 6 volt. So basically this is the solution of this problem. Now move on to the next problem that we have to discuss, like this. This is the circuit. In this example, we have to find the voltage drop between the terminals A and E for the circuit shown below. Here this is the terminal A and this is terminal E. We have to calculate the voltage across this terminal. In order to solve this kind of the circuit, firstly we have to assume the two wires between the terminals where we have to calculate the voltage. Here in this question we have to calculate the AE is the point where we have to calculate the voltage. Let us suppose A having a wires like this fashion and E having a wire like this fashion, and put a voltmeter on it. Let us suppose this is plus minus. So we have to calculate the voltage across this AE. So how we can calculate this voltage should be the summation of this loop. This voltage plus this voltage drop, this voltage source, this voltage drop. If we are able to calculate this loop analysis, then we can easily solve this kind of the questions. So first we have to calculate this drop. This is the voltage source. If we are able to calculate this current which is flowing in this resistance, let us suppose this having a value of 2 ohm, then we can solve these circuits and the current which is flowing in this 2 ohm resistance. So what the procedure is that it is open circuit. This is open circuit because it is a voltmeter. It is open circuit. The 6 ampere is flowing like this. This is also 6 ampere because it is like this fashion. It is open circuited part. If this is a 6 ampere, then it's having a 0 ampere. It's flowing in this fashion. This is a 0 ampere is flowing.